Greetings and welcome once again to my new calculus channel. So I'm John Gabriel, and about 3 or 4 months ago I produced this video on how we got arithmetic from geometry. And so there have been some questions on this topic, and I'm going to clear it up right now and show you exactly what's going on. So it may have been a little confusing to you at first, so I'm going to try to clear it up and make it simpler. So let's begin. By the way, before I continue, also note that a Greek academic has actually explained my idea in one of his videos. So this guy is called Nikos Papoulas, and his video is called The Method of John Gabriel Based on the Elements of Euclid. Okay, so now I want you to understand that book 5 is the beginning of arithmetic and algebra. So everything in book 5 gives rise to arithmetic, algebra, and all the other knowledge and information that you obtain even if you haven't studied book 5. Okay, so book 5 ideally should be studied first. It's also the most difficult book of Euclid's Elements. And the reason I say that is due to the fact that Euclid spends a lot of time on proofs, and Euclid doesn't actually do what I did, which is something that he should have done in his book. He should have explained the arithmetic of ratios. He didn't, but it's obvious that the ancient Greeks knew about it, and I wouldn't have known about it if I didn't study book 5. So nowhere does Euclid mention these things, but I'm going to make it very easy for you to understand now. So let's leave this and come to what is actually happening in book 5. Is the most important things that are happening or what I am about to explain to you. Now, what is a ratio? So a ratio is merely the comparison of two magnitudes. So for example, the comparison of this magnitude to this magnitude, right? Vertical to horizontal. And it doesn't matter if I have it in that position or in that position. Any similar triangle will do, because no matter where we are, I can find infinitely many, and I hate that expression, infinitely many ratios, or innumerably many ratios to this ratio here, right? So I'll explain that in a moment. So no matter where the ratio is situated, so say for example I have, that looks like a half, right? So wherever I move this along here, this representation here is also a half, isn't it? Okay, so let's put it over there. Isn't that a half? Because that is 4/8, right? And so if I move this anywhere, actually I should have done it like that, I'm sorry. This is 4/8. So this here is just, it's also 4/8, but it's not exactly an easy fraction to understand. So I can keep this anywhere longer, even in between, and all these distances here are proportional to these distances. Okay, so if I let this line here denote this ratio, let me just get a pen. So if I call this the antecedent part of the ratio, let's say P, and I call this Q, my ratio is P to Q, isn't it? Okay. And I can find any other ratio by just simply moving this other parallel line to this one, right? So this here again, over here, is an equivalent ratio to PQ. So ST is just another ratio which is equivalent. And so this is basically what you need to know in order for me to explain to you what I'm about to. So let's just close this because I don't need it anymore. And so what I've done here is I'm going to show you arithmetic without the use of numbers. So now if I go ahead and I produce a ratio like that, now remember, if I extend this ratio in any way, let's say I had a line over here let's say I had a line over here, parallel line to this line, let's suppose that this is parallel to this line, then I could easily extend this ratio in geometry by using a compass, right? I could easily just simply take this part, right, and simply add it to this part, right? Or I could take any of these parallel distances and just simply extend this ratio to any of the other lines. So now let me just get rid of that. So let's go back to moving here, and let's say that, go back to what I had here, right? So we can represent ratio 1 as you see there and ratio 2 as you see there. Now these lines here represent the ratios because any line parallel to these lines will equal to one of the ratios, right? So when we find a common consequent, okay, when we want to find a common consequent, we can take a line that is parallel to either of these and just move it along. So you see this, to find another ratio the same as the second ratio, we just move that parallel line until it coincides with the other ratio, the first ratio that we had. So for example, like this, right? Does that make sense? Okay, so in this way, geometrically, just using a compass, even if you like, you can actually do all the basic operations of arithmetic. So let's see how we can do that. So the difference, for example, the difference then will simply be after we've placed these, after we've moved the ratio so that they have the same consequent, right? So now they have the same consequent, and I'm going to just enable the grid. Right. So now they have the same. So to get this second ratio, which was like that, see, to get this second ratio here to have the same consequent as the first ratio, which is this blue line, we have to move this parallel line. So now that is the new ratio, isn't it? So this short green line, which corresponds to this green line, and this orange line corresponding to the dotted orange line. So now we've got the ratios aligned, and we can simply say that the difference is just this line segment diminished by this distance, right? So the difference is just this magenta line, and of course the consequent is this blue line. Now if we take the measures of these ratios, let's show the measures. So naturally this here would be 3/4, this here would be 3/6, and to take the measures, all we do is assign each of the aliquot parts of the ratio, the antecedent and the consequent, a particular number in terms of units, right? So we say, okay, this is 3 little units and this is 4 units, okay? And then all we do is we subtract this green line from this red line, and of course 3/4, it would be 3/4 minus 3/6, which is the same as 2/4, because I've changed this consequence here. I've changed this consequent to be like that, right? So 3/4 minus 3/4 would be 0, but I'm going to leave it at 6 because I actually want 3/6, okay? And that's a half, and this is 3/4. So now, of course, if I had the same distance there, then it's obviously going to be 0, right? Okay. So the next step is to just simply compare these two lines. I don't care about the consequence anymore, and the new ratio will, the difference ratio is this, what you see up top here. So this here is the difference, right? This here is the difference. And when you take the measure, it's 1/4. So in geometry, this is the result, and in algebra, this is the result. Okay? Does that make sense? Right, and then we can also take the sum, all right, which is that, and of course if we show the measures, it would be this line plus this line, or this line extended to this one, so it obviously is 3/4 plus 2/4 is 5/4, and the consequent, which is the blue line, stays the same, And of course the result is 15/12 or 5/4. Okay, I didn't simplify this any further, but I could have cancelled out this fraction. And this is easy to see. When I showed you the similar triangles, all you do is you just take your parallel line and you bring it down to 5/4. Okay, that's all you do. So for example, it would look something like that. And the result, that is, not the ratios, the resultant ratios, which is this ratio over here. And of course the quotient is simply the ratio of this red line to the green line when they have the same consequent, because this orange line is the same as this blue line, right? So this is the division. So this is the same as saying 3/4 divided by 3/6. Okay, and 3/4 divided by 3/6 is 3/2, isn't it? And that's what we do in algebra. Does that make sense? Okay. Now, the product is the reverse of the quotient. So what we'd have to do with the product is we'd have to switch these two around, okay, and then take the quotient. It's always a quotient. The quotient, by the way, is always the product. Is always a quotient, the reciprocal quotient. Okay, so all we do is in geometry is we switch these two around, and not only do we switch them around, but we also find a common consequent. So this becomes this green line, and this line becomes this line here, right? So when we switch them around and we take the multiplication, then we'd have 3/4 times 3/6, which is 3/8, right? Does that make sense? Okay, so that's pretty much it. I've summarized it as much as I could. These are the 4 basic operations, and it all has to do with similar triangles. Remember, you take either ratio and draw a line to it, and then just adjust the other ratio by pulling along the parallel lines. So for example, this ratio here would be the original red-blue ratio adjusted to the same consequent as this second ratio. That's pretty much it. My name is John Gabriel, and this is a New Calculus channel. But before I sign off, please tell your friends about this, subscribe to my channel, spread the news of this channel, because it is the best channel on the web. And then also help me out by contributing to my GoFundMe page. I don't have any other income except what I'm going to be getting from my GoFundMe page. And there really is no hope for me unless I do somehow manage to accumulate a certain amount of money so that I can take care of myself. And that's pretty much it. The links will all be in the details section. I'll place a link to the Geogebra applet, to the Greek video that was based off mine. And by the way, this guy Nikos Papoulas has a lot of other videos in Greek. It's just too bad that he doesn't know English that well, so his videos are all in Greek. But he has excellent videos on physics as well, so you can look those up if you know Greek. And I'll put a link to this as well. And that's pretty much it. So till next time, goodbye.